in the Zoom recording and whatnot for today. And these same kind of calculations are useful to help you out with the dilution activity that you're going to do today. Same kind of thing about Kool-Aid, except the problem is today you made your Kool-Aid way too strong and you need to dilute it down by adding an appropriate amount of water to get to the right molarity. So anyway, if you have these and you want to check your solutions, I think I did them right. I did them quick, but I did them this morning. I did them like 6:30 or something like that. And I'm not awake yet. I haven't had my coffee, but they should be okay, unless I calculated a formula mass wrong or something. So like molarity is very simple. It's just the number of moles of solute divided by the volume of the solution. So if you have like 0.00372 moles of hydrochloric acid and 2.39 times 10 negative 2 liters of solution, you take the number of moles of solute. The solute here is hydrochloric acid, and divide it by the volume of the solution. 0.156 molar. There's three significant figures. If you have a mass instead, this is number 3 is just like the problem yesterday where you're trying to figure out the molarity of the, what do you call it? The Kool-Aid, the molarity of the Kool-Aid solution. You've got to take the number of moles of the solute. In this case, the solute is sucrose, C12H22O11. So if you have a mass, you must convert mass into number of moles. So the 85.5 grams of sucrose, the sucrose has a formula mass of 342.34 grams per mole. So when you convert from the mass into moles, it's about a quarter of a mole. So 0.2498 moles in 1 liter of solution, that's 0.250 molar. One thing I want to mention or note is this is the volume of the total solution. Sometimes, like if you very carefully measure out exactly like 1 liter of water, you put a whole bunch of sugar in it, the total volume may go up. It may end up being greater than a liter. So when it says 1 liter of solution, that means that the total solution volume is actually a liter. And a smart way to be very careful about getting high precision molarity is if you're like, well, I'm going to put 85.5 grams of sucrose into a liter of solution, you don't actually start out with exactly a liter of water. You might start out with like 950 milliliters or something, put the sugar in it, get that all dissolved, and then add water until you get to the total solution volume. Because if you start with the full liter of water and you start throwing a bunch of sucrose in it, that volume could go up, and now you've got kind of an issue where the total volume is greater than what you expected. Then you'd have to like add more sucrose to get the same concentration. So that's the total solution volume. Anyway, so all the time, it's always smart and useful and important to convert to moles for all kinds of stuff in chemistry. There, if you got the mass, you got to convert it into moles anyway. So those are pretty straightforward. In number 4, so you got 14.92 grams of magnesium oxide in 365 milliliters of solution. You know how to write formulas for compounds. Magnesium has a charge of 2. The oxide has a charge of 2. So the formula for magnesium oxide is just MgO, and its formula mass is 40.31 grams per mole. So 14.92 grams, you convert that into moles, 0.3701 moles. And because molarity has to be equivalent to the unit moles per liter, the 365 milliliters has to be converted into liters. So 365 milliliters is the same as 0.365 liters because there's 1,000 milliliters in a liter. And that comes out to be really close to 1 mole, 0.370 moles and 0.365 liters, around 1 molar. You'll see that a lot of solution concentrations, I mean, a really, really highly concentrated solution, there are some acids that have concentrations as high as like 16 molar. That's very, very high. All the solutions that you used in labs up until now, they would be on the order of a mole, 10 moles, something like that. If you ever see or calculate something that's like 100 molar, 1,000 molar, you did it wrong. You can never put like 1,000 moles of solute of anything into a liter of solution. You think that, yeah, you can never do that. That's not going to happen. So on the order of a mole or 10 moles is good. All right, so you've got 4 grams of silver nitrate, and you're trying to make 2 liters of hundredth molar solution. This is a problem that we have in chemical preparation a lot. Like, so, I mean, if I'm prepping stuff for a lab and I'm like, oh, I want hundredth molar, trying to make 2 liters of it. I only got 4 grams. Do I have enough? So the first thing you can do is this mass of silver nitrate, you can convert that into moles with its formula mass. And this 2 liters, that's a standard unit for volume. 100th molar is a standard unit for molarity. The number of moles is equal to the molarity times the volume. So if you take this 0.01 molar times 2 liters, it turns out you need 0.02 moles of the solute. And when you multiply 0.02 moles by the formula mass, it looks like you need 3.4 grams. So the 4 grams is enough. To make 2 liters of 100th molar solution, you need 3.4 grams of silver nitrate. And you got 4 grams, so you're going to have 6/10 of a gram left over. What I might do is just make the whole darn solution up, figure out what's the total volume for 100th molar solution of silver nitrate if I have 4 grams, and then make that total volume of solution up, and then, I don't know, bottle it up and save it. The good thing is if you start with ultra pure water and you take and put solutes in it, you make a solution and you put a cap on it, it'll store for a really long time. We store our solutions for years. Some of the solutions you've used in lab this year may have been prepared 5 or 10 years ago and they're just fine. You just kind of keep using them. All right, so those are the right answers for that. Then 6 and 7 are problems about dilution. So when it comes to diluting something, what's always true is that the molarity times the volume before you do a dilution is the same as the molarity times the volume afterwards. So this is like a molarity times a volume. In today's lab, you've got some Kool-Aid. It's super, super sweet. You've got a very high molarity and a relatively small volume. And the plan is that to lower the molarity, you have to raise the volume. So molarity and volume are inversely related. If you, as a simple ratio, if I write the equation like 2 times 4 is equal to what times 8? Well, this has to be 1. So if the value 2 changes to 1, 4 changes to 8. In other words, 2 times 4 is 8, and 1 times 8 is 8. The first value as a product on the left decreased from 2 to 1. The second value went from 4 to 8. It doubled. So if you've got 100 milliliters of 1,500 molar sodium hydroxide, and I'm going to dilute it to 150 milliliters, as I add water, it's going to make the concentration go down. So it stands to reason that if it was 100 milliliters of 0.15 molar, if I add more water, that increases the amount of solute. It's going to make the concentration decrease. So the formula is M1V1 is M2V2. So much like gas law problems, 1 is like before and 2 is after. So it's a molarity times the volume before the dilution is equal to the molarity times the volume after the dilution. So you had 100 milliliters, that's V1, and 0.15 molar is M1. The final volume is 150 milliliters, that's V2. So all you're doing is solving for M2. And you can leave them in milliliters or you can change them into liters. There I changed them to liters, but if you want to leave it in milliliters, you get the same answer. Because if you go 0.15 molar times 100 milliliters divided by 150 milliliters, it's the same ratio. 100 over 150 is the same as the ratio of 0.1 over 0.15. Let's see, 100 over 150. You still get 0.10 molar. And the last one, so this is exactly the same as the lab. How much water do you have to add to 500 milliliters of some solution that's 0.25 molar potassium chloride to make a 1 molar solution? So I want to make the molarity decrease from 2.4 molar to 1 molar. The deal there is you want to calculate what the final volume's got to be. So if you have 500 milliliters of 2.4 molar, If you decrease it to 1 molar, the final volume has to be 1200 milliliters. Well, you already started out with 500 milliliters of solution. So the problem is, how much water do you need to add? You don't add 1200 milliliters, because if you add 1200 milliliters to 500, you end up with 1700. So if you start out with 500 milliliters, if you add 700 milliliters, you end up with the 1200 milliliters of the final solution. And it should be the correct concentration. When it comes to like Kool-Aid, you can't really taste very small differences in concentration. It has to be really weak or particularly strong to notice if it's not right. It isn't like in a whole gallon of Kool-Aid, if you put like an extra teaspoon of sugar, you're like, oh, that's too sweet. Or if you're short 1 teaspoon, you're not going to notice that little bit of difference because it takes quite a lot to be different. But in chemistry, because it's very quantitative and we're trying to make a correct amount of product from a certain amount of reactant, it's important that the correct amount be measured out exactly right. And it's important to not just know like what is the volume or what is the molarity, you got to know the volume and the molarity. Because ultimately, whenever you calculate one side of this equation, molarity times volume is equal to a number of moles. Molarity times volume is equal to a number of moles of solute. So really, the idea that molarity times volume before the dilution is equal to molarity times volume after the dilution, it's really saying that the number of moles of solute doesn't change. The quantity of potassium chloride ions is exactly the same before as it is after. The amount of stuff that's in the water doesn't change. All you're doing is changing the amount of water. And again, water doesn't have to be the solute, but we call water the universal solvent because it's an excellent, it doesn't react with much. Water is very non-reactive. There's not much that you can put into water to make the water react with something. Water is very non-reactive. Same as like the air you breathe is mostly nitrogen. Nitrogen gas is very non-reactive. It's really hard to make nitrogen react with stuff. So it isn't like you could put things into water and suddenly the water has been reacted with. Only well, some metal ions like sodium ions, they can react with water and cause water to dissociate and make hydrogen gas, but most things don't react with the water. You put sugar in the water, you still got the same water. You can separate the water and sugar and you still got the same water you started with. Okay, so the dilution activity, the idea is we're trying to make some Kool-Aid with the right concentration. The goal is for it to be 0.4 molar, but instead it's actually 2 molar. So that's like 5 times the concentration it ought to be. So anyway, your job is to make a cup of 4/10 molar Kool-Aid. And the disposable cups are on the middle lab table. There's a brand new sleeve of cups. They say like Wegmans cups. A couple things to know. The density of Kool-Aid is not exactly the density of pure water. Once you add solute to a solution, the density rises. One way to know how much solute is in the water is to measure its density. So here, if you have pure water, the density is 1 gram per milliliter. That concentrated Kool-Aid you have, Kool-Aid concentration, its density is 1.06 grams per milliliter. So if you know the mass of this Kool-Aid that's concentrated, you can use the density to figure out, well, if you know the mass of the Kool-Aid, you can use the density to figure out the volume. So in other words, if this has a mass of 37 grams, if you take 37 grams and use the density of Kool-Aid concentration as a conversion factor, that'll get you the volume of the Kool-Aid. Because just like yesterday, you don't want to put the Kool-Aid that you might be drinking into a graduated cylinder because you don't know what was in the graduated cylinder. So instead, you weigh out the Kool-Aid. It's very important not to get the Kool-Aid like spilled on the balances. So anytime you pour Kool-Aid out of the container, don't do it on the balance. Instead, you got your cup, pour the Kool-Aid in the cup, and then set it on the balance. If you dump some of that Kool-Aid on the balances, it's not good. The balances are very expensive. We're ordering a whole bunch more for next year too, and they're not cheap. So the first thing, how many milliliters is 8.5 ounces? 1 ounce is 29.6 milliliters. So that's another conversion. There's a funny thing in our measurement system. Ounce means two things. There's 16 ounces in a pound, and that is for mass, and there's also liquid volumes that have volumes in ounces. Fluid ounce. One fluid ounce is the same as 29.6 milliliters. So the first thing, you want 8.5 ounces of the concentrated Kool-Aid. Every fluid ounce is 29.6 milliliters. And because the density is 1 gram per milliliter, you're going to figure out how many grams of Kool-Aid it's got to be. So anyway, there's space on the front to show how you calculate the dilution and then convert milliliters of concentrated solution into grams. And then on the back, how are you going to plan to dilute it? And then write down some observations about the solution before you dilute it. And then what are some observations about the solution after you dilute it? In other words, what kind of changes take place? And those observations can include like, how it appears, what color it is, its clarity, and then you can taste it as long as you're carefully dispensing from the container into cups and leaving everything in disposable cups. You can taste it. That's totally okay. All right, if you are remote, I put let's see, stuff in the folder. Let's see, show desktop, courses, Chem 1. So in the folder for this week, there's a assignment that says dilution activity. If you're here, you can just turn it in person. Otherwise, when you click on this and you are a remote student, when you click on remote dilution activity, there's some values that are listed that you can use right in the assignment. All right, any questions about stuff? All right. Don't spill stuff on all the balances. Have a good time. Here, so for remote students, yeah, there's values directly right in the problem. And the issue is you're not going to be like making observations about what it looks like and tastes like because you can't like look at it and taste it. So anyway, 8.5 ounces, how many milliliters is that? Your goal is to dilute the solution from, it starts out as 2 molar. And you want to get the concentration down to 0.4 molar. So once you know how many milliliters 8.5 ounces is, the 8.5 ounces of volume in milliliters is associated with the 2 molar solution. The goal is to figure out what the total volume needs to be if the concentration is 0.4 molars. And that's the same calculation as like sort of like number 6 and number 7 with a equation for dilution. Let's see, more chat. Yeah. If you have questions, you can put them in the chat.